All right. Hello, everyone. Thanks to everyone for tuning in. Let's see. My name is Alex Ferencic. I am a postdoctoral researcher at UC San Diego, and today I'm going to be doing some work with FPGAs. So I have here a let's see. This is an Exablaze X25 FPGA-based NIC, and we're going to be doing some work with the transceivers. All right. So first off, I have, I suppose, a couple of announcements. I set up a Patreon a little while ago, so if you like what I do, either in terms of the streams or the open source software development or whatever, feel free to go, express your support. Let's see. I guess we might as well get into what the content is going to be for today. So this is a problem that I've been running into for a while with just the Ethernet interfaces on a lot of these FPGAs. And before I get into kind of the the background part, the first thing I'm going to do is demonstrate what the issue is that I'm trying to solve, and then we're going to go over some background information and then take a crack at seeing if we can fix the problem. All right, so like I said, what I have here is an Exablaze Exanic X25 FPGA board. This has a Kintex UltraScale, Kintex UltraScale Plus FPGA on it, XCKU 3P. And I'm using this one because it's a pretty small FPGA, so it doesn't take too long to build a new configuration for it. Okay, so what we have hooked up to this is a connection to a 10 gigabit NIC in my desktop computer, and the design running on the FPGA is basically an instrumented version of my Verilog Ethernet design. So it's just, it has PHYs on both of the ports here, and then connected to this one there is a 10 gig MAC and then the UDP stack, right? And the block lock outputs from the PHYs are placed on these two LEDs over here. So as you can see, we have one good 10 gig connection that's showing up here. Pretty straightforward. All right. So on my computer over here, if I can switch, let's see, to that, I have Avado running that's connected to the board over JTAG, and we have both an ILA that's connected and a VIO module that allows a couple of signals to be controlled and monitored. So again, looking at the SFP1 connections, we can see that the block lock is high, bad block is low, everything looks good. If I run this, I'm going to go over what these signals mean a little bit later, but this is how it looks when the connection is idle, right? We have a valid link, but there's no activity. All right. So let me go ahead and switch back over to this, and let me show you what's going on here. All right. I unplugged it, but we still have a link light. That's a problem. Question is, why is that happening? All right, so if I go back over to here and I rerun the ILA, we can get a view of what's going on inside. The first thing you'll notice is that this is the signal coming out of the transceiver, out of the serializer on the FPGA, and we're just seeing AAAAAA, which is 01010101, right? It's just this repeating bit pattern. And the way the block lock component works is it's just looking for this little 2-bit sync header that's either 01 or 10, and because the pattern is just repeating 010101, every position looks like a sync header. So it says, oh, I have a lock, but it actually doesn't. And the thing that's generating this this bit pattern is something inside of the transceivers on the FPGA itself. Let's do a little bit more poking around and see if we can get any other interesting behavior out of this before I go into the background in terms of what I suspect is causing this and some potential solutions for fixing the problem. All right, let's see here. If I plug that in again, I think that's probably is a valid link. Check on the IL. Yeah, okay. I have another connection here. Yeah, it likes leaving that link light on here. So this connection is going to a Mellanox ConnectX-5 NIC. And this one tries to come up at 100 gigs first. So the light goes out and then it comes back on as it negotiates up. And it's doing the same thing, leaving the light on when you unplug the connection. All right, let me take a look at this here. Yeah, so this one basically came up exactly the same. I reran the ILA, and we are seeing exactly the same thing, except in this case, instead of AAAA, it's 5555, so that's either inverted or shifted by 1 bit, however you want to think about it. Let's see. I've had two things happen that are somewhat perplexing. One of them is you'll get no link light when there's a cable plugged in, and in other cases you'll get a link light when there's a cable plugged in, but the link won't work. I'm going to see if I can get it into one of those states. I'm not sure if it's going to cooperate. I do have a second PHY on here. I don't think it's not hooked up to the ILA, so I can't look at what's coming out of that. So far, it seems to be well behaved, aside from leaving the link light on when it's not supposed to be. I'll try this for another few seconds and see if I can get it to do something interesting. Let me try the other NIC, which will have slightly different signal characteristics, and see if that makes a difference. Yeah, so far, the only thing that we've been able to see so far is a false block lock indication when there's no cable plugged in. That's pretty reliable. That happens quite often. Yeah, I'm just getting idles out of this thing. It's not getting as hung up as I thought. It seems like some of the FPGAs are more sensitive to this than the others. The Ultrascale ones in particular seem to be more sensitive than Ultrascale Plus. I'm not sure why. I was thinking about doing this with the with an Exynic X10 that I have, which is an Ultrascale FPGA, a KU035. And that seems to be basically every time you plug something in, you got to reset it. This one is a little bit better behaved. Anyway, this is still a bug. We still need to make sure that this thing is resetting itself when there's no link connected. Let me just try another little bit more poking around here. For whatever reason, this is not working how I was expecting it 100%. I was able to pretty reliably get this into a bad state yesterday, but now that I have the camera set up, the only thing we're getting is a block lock indication when we aren't supposed to have one. All right, so this time I'm seeing something a little different on the ILA. This is not a bug necessarily, but this is showing something other than idles going down the line. So we'll take a look at what this means in a little bit. But that's just an error indication from the NIC, basically. Yeah, but that link still came up properly. All right, I'll try one more time here. Let's see if I can get this into a funky state. No, I think that's working okay. Oh, all right, I did get into a weird state. Okay, there we go. Okay, so take a look at this. In the ILA, we're seeing all A's here, right? It looks like we don't have a valid signal connected. But if we look at what's coming out of the camera here, right? What the board is actually doing, we have the link light on, right? So it says there is block lock, there is a cable plugged in, but if you look at the ILA, you know, this is not valid data here, right? This is not showing a usable link, right? So this is a problem. And the question is, you know, what do you do about that? Well, a couple of things, right? The first question is, what is happening? If we figure out what's going on, then you might be able to find a solution. All right, so in order to get our head wrapped around this, we need to take a look at what is going on the FPGA. So the setup that we have here is we have a 10 gigabit NIC in the host machine, and that is connected to the FPGA via this direct attach copper cable. So the NIC in the host computer is generating, you know, the transmit end of a 10 gigabit per second Ethernet link, and then this card is receiving that. So I'm assuming that the NIC on the other end is, you know, well behaved and doing what it's supposed to do. But something is not working correctly on the FPGA end. All right, so let's take a look at the documentation for the high-speed serializers in the FPGA. Right, so this is the manual for the GTY transceivers on the FPGA. And for those of you not familiar with these, there are several components inside of these. Right, so there is, let me find the block diagram here. Right, so on the FPGA, these transceivers are provided in groups of 4 called quads. Each quad has 4 transmit and receive channels and a pair of shared PLLs. So each channel also has its own local PLL. These only go up to like 12 gigabits a second or something like that. The quad PLLs go all the way up to the full line rate supported by the transceivers. So the transmit side forms the output, and the RX side forms the input. So, I mean, in this case, we're technically using both, but we're setting aside the transmit side. We're only going to focus on the receive side. Inside of each one of these channel modules, this is what it looks like. So we have the FPGA fabric logic sits on this side, and this side is connected to the optical modules, or the SFP pluses. Let me zoom in a little bit here, and we'll take a look at all of the components that are inside of these modules. All right, so in the transmit direction, we accept parallel data from the FPGA fabric here, and then this travels through the PCS logic. So all of this is, you know, pure digital logic. Now the PMA, this is the part that actually runs, you know, at line rate, and this is the analog part. So this is where all of the, you know, analog black magic takes place. This here is just pretty straightforward digital logic. Right, so the data comes in, it goes through the transmit asynchronous gearbox. The output of that is then sent through the serializer and out the door. For 10 gig Ethernet, we don't really use any of these other components. So this is used for PCI Express. Well, I guess also that one. There's a TX pipe control, right? That's you know, configuring the internal data path here. Pattern generator used for testing stuff. There's a TX synchronous gearbox, but for 10 gig Ethernet, we're using the asynchronous gearbox. So the asynchronous gearbox allows you to bring in 66 bits here, and then it converts it to 64 bits for actually sending that out on the wire at a different clock. Right. And then this is the actual serializer, right? Parallel in, serial out. And then there is the output driver. So this has a TX driver. It has some components for out-of-band signaling and components for pre-emphasis, so that you can improve the signal quality going over the link. That's the transmit side. I'm not going to go into too many more details about this. On the receive side, we kind of do all the same stuff in reverse. You come in with a pair of pins here, you go through the receive equalization. So there's a linear equalizer, there's a DFE, which is decision feedback equalizer, and then the output of that goes through a serial to parallel conversion, and this is the deserializer part of the operation. And then the output of this is parallel, which then goes through the receive PCS. Again, this is the analog stuff, this is the digital stuff. Right, so the data comes out here, and in the case of 10 gigabit Ethernet, we basically bypass all this stuff, go through the asynchronous gearbox, and then go over to the fabric logic. Everything else here is for other protocols. So 128.130, that's for PCIe. AP10B, that's used for PCIe and for other protocols. COM detection and whatnot, that's part of AP10B. Yeah, and there's also PRBS checker for, you know, testing stuff, basically. These two are connected with some loopback connections that are also for link testing. Anyway, the focus of today is going to be what's going on in the analog front end here. Because what we're getting out of this thing are these strange bit patterns. So where are they coming from? They're not going to be coming from the NIC at the other end, right? Because that's going to be sending, you know, valid 10 gig data. So they're not going to be coming from the link itself. They're going to have to be introduced by something inside the receiver. There's nothing in here that can really generate bit patterns. It just gets passed through. So that leaves us with basically the analog front end, and something in here is not working correctly. And what I suspect is going on is that this has to do with the decision feedback equalization. So let's take a little look at what takes place in the receiver. Okay, so when the signal comes in, it goes through, do we have a more detailed, no, it doesn't even show the CDR on this one. That's interesting. All right, so let's see, here's the analog front end. This is, oh yeah, I don't want that. Where's equalization? CDR, okay, here we go, RX equalizer. All right, so after the signal comes into the input pins, it goes through the terminator resistors, and then it goes through the equalizer before it hits the serializer. The equalizer is responsible for attempting to improve the signal quality on the link. So with these really high-speed connections, the situation that you run into primarily is high-frequency loss. There's a few other effects as well in terms of, you know, impedance discontinuities and stuff like that, but for the most part, the real killer is the high-frequency loss. And what happens with high-frequency loss is, you know, where is all of that high-frequency information in the input waveform, right? It's all in the edges. If you have a sharp edge, that indicates you have a lot of high-frequency information there. So if you lose high-frequency information going down the link, then what happens is all of those edges get smoothed out. And this does several things. The main thing is it creates something called intersymbol interference, where previous symbols will affect the shape of subsequent symbols. So if you want to build a reliable link, you need to do something to try to mitigate some of that intersymbol interference and high-frequency loss. One technique is to use a linear equalizer. And the idea here is you have basically two different gains. You have a low-frequency gain, high-frequency gain, and then what you do is you look at the signal quality, and you have an adaptation controller which adjusts these two gains to try to optimize the signal going into the serializer. If you do this right, then you can get a low bit error rate that gets handed off to the PCS for the receive. But there's kind of a limit to how much you can do with linear equalization. This basically just affects the frequency response. But if the signal is really smeared out, then you need a different approach. And this is where decision feedback equalization comes in. Now, this block diagram looks really complicated, but it just has a bunch of repeated stuff here. The idea behind this is to try to take into consideration the effect of the previous bits. Right, so the signal comes in here, we have a small amount of linear equalization, and then we take the signal and we offset it by this, which I'll talk about in a second. The offset signal gets threshold detected, right? So at this point it's an analog signal. After this it's digital, it's either high or low, and then that gets handed off to the serial to parallel conversion. Right, the output of this also gets shifted down all of these shift registers. So we're basically looking at the previous, I don't know, what is this, like 15 or 16 bits, something like that. And then what we do is we take the output of each one of these, and we have a little controllable voltage source, basically, and we add all of these up, right? So if this bit is set, then we use the positive version of this. If this bit is clear, then we use the negative version of this. All these get added up, and that ends up offsetting the input signal. So this has the effect of, moving the sampling point around depending on the previous bits that we've seen. So for example, if you get a bunch of, 1 bits, then you should probably look a little bit higher for the next bit to detect the threshold more reliably. So that's kind of the point of DFE. And this is a simple part, the actual equalization, but how do you determine all of these parameters, right? This can change over time as the voltage and temperature change in the transmitter to the receiver. That's going to change, how the analog components work. If the cable gets bent or moved around, that can change the signal quality through the cable, things like that. So this, you have to continuously adjust these parameters. So there is adaptation logic on the FPGA, this MMSE adaptation controller, and this looks at the signal quality here and then adjusts all of these parameters to try and optimize the signal at this point to minimize the error rate. So I'm not sure exactly what's going on in here and exactly how this works. There's probably kind of standard ways of doing that you can, find if you go searching around for that. But because this is looking at the signal quality here and trying to, optimize the signal, this only works if you actually have a valid signal coming in, right? If you have no signal coming in, then this is going to try to, improve the quality of, well, nothing. And if you have garbage in, then you get garbage out. And the garbage out here doesn't just come in terms of, random data, but it comes in terms of, useless parameter settings here. And what I suspect is going on is that if one of these gets set with a large enough negative value, you end up generating, repeating bit patterns. So for example, if this gets a large negative value, then let's say this is 0, this will drive a large negative value, which will move the sampling point down and result in this reading as a 1. Then this will flip to 1, this will produce a large negative value, this will move the sampling point up, right? Or, yeah, so that'll read slow. Hang on a second. So you need some negative, what do you need for oscillation? You need some delay, and you need some, negative gain, right? You need an inversion. If you have a positive gain, you get a positive feedback loop, it runs into the rail. If you have negative gain, then it'll oscillate. So what happens here is if this was 0, right? If this was 0 here, then this will produce a large positive offset, right? That will push this up over the sample point. So this will read as 1, right? That'll get stored here on the next cycle. That'll then produce a large negative value, which will push the sample point down. It'll read as low. And it'll put a sample point down, so it'll read as high, and then it will oscillate, right? So every other cycle, this will go high, low, high, low, high, low, and this will produce some bit pattern. Then the problem is, if you do add a signal later, that input signal could be a lot smaller than this oscillation that you have running around in here. And the adaptation controller won't be able to, work its way out of that hole basically and start producing a valid output signal. So this is what I suspect is going on here. The solution, I think, is going to be simply to reset the DFE logic in the transceiver. So let's see, I have Avado running over here, and let's see, is this still wedged? Probably is. Okay, yeah, so this is outputting a bit pattern of 5, 5, 5, 5, 5, 5. We still have the cable plugged in, right? There we go, we still have it plugged in. Okay, so what I'm going to do is I'm going to reset the transceiver. All right, so I want to do RxPMA reset. All right, let's take a look. We'll watch the link light as I reset that, right? I'll set it high. And then I will set it low. Interesting, the link light didn't go out at all, but it's still lit. All right, let's take a look at what the ILA says as a result of that. And there we go, we have a link. Again, we're back to just normal idle data. Right, so that seems pretty straightforward, right? When it gets stuck like this, the problem is most likely coming from something inside the transceiver, presumably the DFE, but maybe there could be something else going on. And what you need to do is reset it. Okay, cool. So how do you know when to reset the transceiver? That's the trick now. Okay, so to figure that out, I actually spoke with Xilinx a couple times about this to see, okay, is this a common problem people have, and what's the general solution to that? And it basically just ends up being protocol dependent. So what you need to do is be able to look at what's coming down the link and make a decision whether or not the link seems to be working correctly. And if it isn't, then you reset it. All right. So to get an idea for how to do that, what we need to do is take a look at the Ethernet specification, which talks about exactly what's going on over the link. And with that information, we should be able to come up with a method for resetting the transceiver based on what's coming out of it. All right, so this is IEEE 802.3. If you want to download this yourself, it's available on the IEEE website. They have their IEEE Git program, and you need to create an IEEE account. You don't need to be a member, but you need to create an account, and then you can download a couple of standards that are part of this program for free. So the Ethernet standard is one of them. It's a good thing to have. It also is good bedtime reading. That at 5,600 pages, even if you have some insomnia, it'll probably still work. Okay. So what we're going to do is take a look at the 10 gigabit per second section, because we're using 10 gig Ethernet. All right, so I'm not going to go into too much detail about all of this, but what we're going to be focusing on is kind of the physical layer portion of this. All right, so the Ethernet specification is divided into a whole bunch of different layers. So this is kind of similar to how you have the OSI, networking model. In Ethernet, you have the MAC, or the media access control here, and then that's connected to the physical layer interface, or the PHY, down here. And then that's hooked up to the actual, cabling or fiber or whatever, the medium. All right, so, and then above this, you would be connected to the host through, PCI Express or whatever, and then you'd have the operating system and network stack sitting on top of that. Or in the case of an FPGA, that would be your user logic. All right, so I'm not going to talk about the MAC, but we are going to take a look at the connection between the MAC and the PHY, and then the PHY itself. All right, so for 10 gig Ethernet, the connection between the MAC and the PHY is something called XVMI. MII stands for the Media Independent Interface, and this was, originally developed for like 10 megabit Ethernet. So MII is 4-bit it's a 4-bit interface, so you have 4 bits for transmit, 4 bits for receive. Pretty straightforward, and plus a couple of additional signals. GMII for Gigabit Ethernet is an 8-bit parallel bus, right? 8 bits for transmit, 8 bits for receive, running at 125 megahertz. XGMII is for 10G, and it's a 32-bit bus, double data rate, running at 156.25 megahertz. And the X here is the Roman numeral for 10. Just FYI. It's not random. Okay. So that's the connection between the Mac and the PHY. The PHY then consists of several internal layers. So there's the PCS, and that is different depending on what the standard is. And then there's the PCS is the physical coding sublayer. The PMA is the physical medium attachment, and the PMD is a physical medium dependent. And then you have the actual medium. So the PMD is basically the optical transceiver for 10G base R. The PMA is, like the serializer on the FPGA or whatever device you're using. And the PCS is, the digital logic that's doing the encoding and decoding and whatnot. Right, so the main thing we're going to be looking at is as what the PCS is doing. Because on the FPGA, the PMA and the PMA is in hard logic, right? Those are the actual serializers, the GTY sites, and the PMD is plugged into the board. So the only thing we can control is the PCS and everything above that. So the hope is that we'll be able to look at what's going on at the PCS layer and figure out whether or not the transceiver needs to be reset. All right, so before I get into what's going on at the PCS, we'll take a brief look at XGMII. All right, so XGMII is, like I said, the interface that connects the Mac to the PHY. And there's a couple of variations on this. XGMII, it was originally developed kind of as a chip-to-chip standard, right? So you have your Mac IC and your PHY IC, and then you have the XGMII link in between the two. But it's not used that way anymore. I don't know if anybody even makes XGMII PHY chips anymore. Because this is, like I said, a 32-bit parallel interface running at 156 megahertz. It takes up a lot of pins and a lot of board area, so nobody uses it chip to chip. But it's a pretty common interface to use on chip for interconnecting, a Mac to a PHY. So, if you look at, say, the Xilinx PCS PMA IP core, it has an XGMI interface on one side, and for chip to chip, it's designed to be a 32-bit parallel interface at 156 megahertz, running double data rate. But doing stuff on chip, you never do anything double data rate. You always do it single data rate. So for XGMII, you're basically going to see two flavors. One is running at 32 bits at 312.5 megahertz, exactly the same, but double the clock. Or you're going to see an unwrapped version where it's 64 bits wide, running at 156 megahertz, where you're basically transferring 2 cycles of XGMII for every clock cycle. That's pretty straightforward. There's another interface that you'll see occasionally called XVMI, and this is basically the only chip-to-chip thing that you'll see for 10G PHYs that's not actually running at 10G. So, and you can actually see this on some NICs. So let me take a look really quick at a couple of different NICs. All right, let's see. We have, for example, I have a Miracom 10G NIC here. And this one is basically 2 NICs on one board. There's literally a PCIe switch here that makes the connection. So let's see. For those of you that like looking at boards, I need something to point with here. We can go over what's on here real quick. We've got PCI Express. I believe this is a Gen 2x8 interface. And then that's connected to this PCIe switch chip. And then between the switch chip and the 2 NIC chips, there's a whole line of capacitors here, right? There's 2 lines, there's 8 little pairs here and 8 pairs there. So that indicates that we have 8 lanes of PCI Express between each of these chips, right? And I believe that's 8 lanes of PCIe Gen 1. but I would need to check in LSPCI. I haven't plugged one of these NICs in a while. I can't remember exactly what it is. There's also a chip over here. This is a clock buffer. So there's a 100 megahertz ref clock from the PCIe Edge connector. So this replicates that 3 times for these 3 chips. All right, but the main thing we're looking at today is not the PCIe side. It's the Ethernet side. So on this board, we have a pair of SFP plus interfaces, and they are connected directly to these NetLogic PHY chips. So these are the AEL 1010 PHY chips. And if you look, you can see there's 2 little pairs of traces that connect the PHY chip to the SFP module. So those are going to be running at 10G, obviously. But on the other side, what's the interface? Well, we see 1, 2, 3, 4, 5, 6, 7, 8 pairs of capacitors. Well, that's for your XVMI link, right? We've got 4 pairs that are connecting these guys together. And for maybe a slightly different look at the same thing, this is a different NIC that I have. This is, what's the manufacturer of this one? It's a QLE 8240. I don't see a manufacturer logo. I think it's a QLogic. This one, it's a single port NIC, but by looking at the board, you can tell that they use the exact same board for the dual port version. In this case, we can actually see the traces that are wired up here. Well, so this one has a single NIC ASIC on here. Might be able to see that under the heatsink. We've got 8 lanes of PCI Express that goes to this guy, and then that's hooked up to the QSFP modules via a couple of PHY chips. Right, so over here we can see the PHY chips coming off of the connector for the SFP Plus module. You get 2 of those routed over to the site for the PHY chip, and then we have 1, 2, 3, 4, 5, 6, 7, 8 pairs that are running off to the NIC ASIC here. So that is XVMI, right? We have 4 pairs for transmit, 4 pairs for receive. And for more modern NICs, such as this Intel, what is this? X520, they just have 1 chip on here, right? It doesn't have XVMI, it just has an internal connection. So there's 8 lanes of PCI Express to the ASIC, and then these are directly connected to the optical modules with no other chips. You can see there's just 1 chip under there. Right. So usually these things are used internally. All right, let me switch back over. Okay. So yeah, usually these interfaces are going to be used internally. Occasionally they are used externally, but it's not super common these days because it's not too hard to run 10 gig over boards. All right. So let's take a look at what XVMI looks like, because the PHY is basically just taking XVMI and repacking it and re-encoding it into the data that's actually sent over the link. All right, so XVMI, like I said, it's a 32-bit interface. It's divided into 4 byte lanes. And actually, in each direction, you don't have 32 wires, you have 36, because there are also these 4 control connections. And these control connections indicate whether each one of these byte lanes contains control information or data. All right, so go down a bit further. There is here we go, a little timing diagram that indicates how you transfer a frame across an XVMI interface. So you start, well, okay. Let's first take a look at the control characters, right? With TXC low, this indicates that you're sending data on that lane, right? So TXC 0, this is normal data. Okay, if TXC is 1, then that indicates that you're sending some kind of control information. And there's only a couple of control characters that are used in XVMI. There's 07, which is idle. There's FB, which is start, FD to terminate, FE for error, and then a couple of additional signals, or a couple of other additional encodings that are used for other purposes. So like 9C is sequence ordered set. And there was another ordered set indication as well. I can't remember. It's not in this table though. Probably in a different table. There's also 06, which is for LPI. So most of the encodings are not used. But the main ones you need to know are idle, start, terminate, and error. All right, so if you want to send a frame over XVMI, the way it works is you send a start in the first lane, right? And then you send the frame after that. So for Ethernet frames, you send 8 bytes of preamble, including the starter frame delimiter. So in the first lane, you have the start control character, and you can look at the TXC here, and this indicates it's just 1. So that means that's a control character, and the other 3 are data. And then subsequently, it's all data. So you get your start, you get, well, this replaces the first byte of the preamble, and then you have 6 bytes of preamble, and then the starter frame delimiter, and then the actual frame. So you'd have your Ethernet header, and the IP header, and the frame data, and yada, yada, yada. And then at the end, you have the frame check sequence, and then the terminate control character, and then you go back to idle. And if you look at this hex C, that means 0, 0, 1, 1. These first 2 are data, the second 2 are control. Everything works. The only lane that you're allowed to send the start control character in is in lane 0. So I think that says it over here somewhere. Start only valid in lane 0. Right. So you can see on this timing diagram that this is supposed to be a DDR interface where you're transferring data on both clock edges. So this is only done this way when you're doing, board level connections. If you're working on, on chip, then you're not going to be doing DDR. You're either going to be running this at double the clock frequency at 312.5 megahertz, or you're going to be transferring two cycles basically of XVMI at the same time. So when you do that, when you have 8 lanes, then you can put the start in either lane 0 or in lane 4. And then you transfer at 156.25 megahertz. All right, so that's XVMI. The Mac generates XVMI data and hands that off to the PHY, or in the reverse direction, the PHY will hand XVMI data off to the Mac. Now, what is the PHY doing? Or at least, what is the PCS layer of the PHY doing? We're going to take a brief look at the 6466 encoding that's used by the PHY layer. All right, so let's see here. There is okay. Here is a little diagram of what's going on in the PHY, or in the PCS layer. So you accept 2 cycles of XVMI coming in. And the weird thing is this doesn't show the TXC because there's 72 bits coming in, right? You got 32 bits for the first cycle, 32 bits for the second cycle, and then you've got 4 bits of control information for each of these. So you take all those 72 bits that come in, and then you encode that into 8 data bytes, 64 bits plus a 2-bit sync header. Then this set of 8 bytes gets sent through a scrambler. This is a linear feedback shift register based scrambler. The output of that you then combine with the sync header, and then that gets sent out on the wire. This one specifies explicitly a 16-bit interface to the serializer, but I think that's kind of an implementation detail. So on the Xilinx devices, the serializers are set up to accept, well, in this particular case, a 66-bit input. So the gearbox sits inside of the transceiver. So basically the PHY layer, or the PCS layer, kind of ends here, and then the rest of this takes place inside of the hard logic in the transceiver. All right, so that's for the transmit direction. For the receive direction, you do the exact same thing, but in the other order, right? You get the serial data that comes in, you do block synchronization to identify the sync header and get that in the right spot. And then you take the 8, the 8 data bytes here that you have, you descramble those, and then you decode those into, 2 transfer cycles for XVMI. You also take the sync header into consideration, and you'll generate the control lines as well. All right, so that's kind of an overview how that works. This table I'm going to go over in a minute that shows all of the block encodings. But this table shows all of the control codes that are supported by 6466 encoding. And one thing you'll notice is that the set of control symbols is actually very small, right? There's idle, right? That's the same. There's LPI, right? That gets passed through. Start and terminate, they don't exist. I'll get to that in a minute. Those are never sent as, actual symbols. They don't have defined encodings. And then there's also error. And then there's a couple of ordered set indications as well. So sequence ordered set encoded by block type field plus O code, and then all these reserved symbols. I don't know what these were used for. They must have been used at some point because the PHY is supposed to translate those. Anyway, how do you take XVMI and encode it into these fixed 66-bit blocks? Well, there's a couple things that need to be done. The idea here is to do a couple of things. One of them is that we don't want to transfer all of those control signals, right? We're taking 72 bits and we're trying to compress it down to 66 bits. So we have to find a way to transfer that control information somehow, and more efficiently. And there's a couple different techniques that are used to do that, right? The first one is we take advantage of the fact that the encoding for XVMI is relatively fixed, right? There's two places you can put a start control character, and those are the only two places, right? Well, because we're pulling in 2 cycles, then there's 2 possible positions, because in each cycle there's only 1 possible position. And then outside of that, there's a limited number of ways you can pack in the data symbols. So what it boils down to is when you're sending just straight up data, you just send the data, right? So inside of a frame, you just send the data in blocks of 8 bytes, and you attach a sync header 01, indicating that this is data. For everything else, you use one of these fixed control formats, right? So for all idles, you use sync header 10, use block type 1E, and then you just send all 8 control characters. And what they did here is they stole 1 bit from each control character. So you're only sending 7 bits for each one of these, and then you have 8 bits for the block type field. Right, so that's the control characters. And then there are a number of ordered set encodings. These are used for passing, error and status information from the device at the other end of the link, in-band over the link. And then we get down to the start and terminate control characters. So we have 2 encodings for start in lane 4, right? So this one is, this will be like 4 idles, then a start, and then 3 data bytes. This one is an ordered set, and then a start and 3 data bytes. And you'll notice that there is no start control character that's actually sent, right? You send the idles, and then you send the data, and the block type implies that we have a start in lane 4. And same thing for this one. And then there's another one for start in lane 0, right? So we don't actually send the start, we just send block type 78, and then we send the 7 succeeding data bytes. And then we get down to the terminate control codes. These are, again, the terminate control character is never actually sent. You use the block type to indicate how many data bytes are being sent, and then you pack the rest with the control characters. So we have terminated in lane 0 all the way through terminated in lane 8. So there's 8 control characters here. So if you're going to send a packet, it's very simple. You send idles, right? Using this block type 1E, idle, 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 until you reach the start of the packet. And then you send one of these start control characters, probably this one, right? Start in lane 0, and then the data. You send the start, like I said before, it replaces the first preamble byte. So the entire preamble and starter frame delimiter is packed into this first cycle. And then you send the packet data, right? When you reach the end of the packet, depending on how much data you have left, you then send one of these terminate blocks, which can carry either 0, between 0 and 7 data bytes at the end of the frame. So that's how you can send, arbitrary sized packets over Ethernet. All right. So the goal for what we're trying to accomplish today is to figure out whether or not we're looking at, valid traffic coming out of the transceiver, right? So the idea is that if we see invalid traffic for, extended period of time, then we probably need to reset the DFE on the transceiver and, let it relock. So what are all the things we could look at? Well, the first thing is you can look at the sync header, right? If you see a sync header of 00 or 11, well, then there's a problem. And currently the block lock synchronization components are looking at the sync header already. So obviously that's not sufficient, but it's a start. Right, so one thing we can do is look at the sync header. Another thing we can do is look at the contents of the actual data, right? So unfortunately, there's not much we can do for something that decodes as actual data, right? Because you can send whatever arbitrary data that you want. So we can't validate anything based on the data. But what we can do is take into consideration that there's a maximum amount of data that you can send at any given time, right? So for example, Ethernet usually has a maximum transmit unit, or MTU, of 1500 bytes. So you can't send a block of data larger than 1500 bytes before you have to end the frame and start a new one. And when you do that, then you're not sending data anymore, you're sending some control characters. 1500 bytes is not the largest MTU. There's also jumbo frames that are like 9K, so you wouldn't want to set the limit at 1500. You'd probably want to set it at, hundreds of kilobytes or something like that. So that if you have, an extended period where you're only seeing data symbols, okay, now you know that there's some sort of a problem. We have to reset the link. Right. So that's one thing that you can look at. Another thing that you can look at is the block type field, right? There's a limited number of encodings for this. If you see one that's not in this list, well, obviously something got screwed up. And you might want to consider resetting the transceiver. Now, another thing I should mention is that it's expected that occasionally you're going to get some bit errors, right? So a bit error could give you a block type field, but usually that's going to be kind of a transient thing. So if you just see one bad block type field, you don't want to reset the transceiver. You have to see enough bad block types within, a certain period of time before you can make the determination that, yeah, there's something wrong with the transceiver. We need to reset it. Right. What else are there? Another thing you can look at are the actual control characters themselves. So for sending idles, but this is not, all zeros, then that indicates that there's something wrong, right? And maybe you want to consider resetting the transceiver. So we can look at the block type and we can look at the control character encodings. But there's another potential issue here. Every time we have a lot of data bytes, that's kind of less coverage that you can look at, right? So if you look at, say, termination in lane 7, for example, right, we have a bunch of data bytes. If we happen to get a bit pattern that sets this prefix and we lock onto that, then all of these are going to look like valid control characters. But at this point, you can start looking kind of at the context, right? You don't expect to see these characters back to back, right? You should see one, and then you should see either idles, or you should see, start a frame indication, right? One of these start control characters. So what we can do is track whether we're in a frame or not. And then if you're in a frame and you see a start control character, then you know that's an error. Or you're outside of a frame and you see a terminate control character, well, then you know that's also an error, and you probably need to do something to reset the transceiver. Right, so what I want to do today is look at writing a little Verilog module and potentially make some modifications to the PHY modules that will permit checking more of the on-wire format to make sure that we're seeing what we want to see, basically. that we're seeing, you know, a valid signal. And if we aren't seeing a valid signal, then we can, you know, kick the transceiver and reset it. All right, so now that we have a little overview of what's going on here, let's take a look at Vivado again. And we'll take a look at the signals that we're seeing here, because what I've done is I've instrumented the PHY at a couple different points. The PHY module that I have consists of a few different modules. Let's take a brief look at that. This is the top of the PHY module, and this has an RX side and a TX side. So for today, we're really only interested in the RX side. Inside of the RX side, there's basically two modules. There is the receive interface module, and then there is an XVMI base R decoder module. So the interface module is kind of the component that's closer to the actual serializer. And this one is responsible for accepting data from the serializer, performing the, you know, block lock routine, which involves commanding the serializer to slip to subsequent bit positions when it's trying to find the proper alignment. And let's see, and this is also responsible for doing the actual scrambling. We can actually take a look at a couple of these other functions real quick here. Where did that go? So I mentioned the Scrambler. This is what the Scrambler looks like. It's a very simple linear feedback shift register Scrambler. And the reason I use this one is because it's self-synchronizing, right? You don't need to do anything to get this synchronized at the other end of the link. So the descrambler, it just looks like this. You take the previous 58 bits, and from that you can descramble subsequent bits. So once you get block lock, the first block is going to be screwed up, but then after that they will all be descrambled. But there's a problem with this kind of descrambler, and this is the reason why they use different techniques for newer standards, and that they don't use this type of scrambler for things like PCI Express, and that's that it spreads out errors, right? If you get one bit error, obviously you get one bit error here, but then 39 bits later you get another bit error, and 58 bits later you get another bit error. So this is not good for when you're using things like forward error correction, because every bit error that you get over the wire, you now have to correct 3 bit flips. So that's a problem. And as a result, different techniques are used when you're using FEC. Right, so that is the Scrambler, and then there's one other component that we can take a quick peek at, and this is the block lock routine. This is how you actually locate those sync headers, right? Because you have a transition every 66 bits. It's either 0, 1 or it's 1, 0. And you have to be able to locate that. And they have a very simple routine for doing that. Basically, the idea is that you check the sync header, right? And if you see enough valid sync headers, then you say, oh, we have block lock, right? Otherwise, if we see an invalid one and we see enough invalid ones, then you slip the serializer to the next bit position. So this is how this works. You start out in reset, where you clear out all the counters. There's a counter for the number of sync headers that you've seen. There's one for how many invalid sync headers that you've seen. And I'm not sure what this slip done thing is. All right, so you start out in this state. Oh, and then you also start out with block lock set to false. Right. Okay, so block lock is false. Both of these counters are 0, and then you check the sync header. If it's valid, then you increment the number of sync headers that you've seen, and then you go back here to test the next one. So you'll basically loop around here until you see 64 good ones and no bad ones. If that's the case, then you set block lock to true, and you're basically done. I mean, this is running continuously, so you're continuously checking the sync headers. But that's the idea. Okay, what happens if you see a bad one? If you see a bad one, then you go over here, you increment the number of sync headers that you've seen, you increment the number of invalid sync headers that you've seen. And then if we're not locked, then we immediately slip, right? Move to the next position, reset the counters, and we run it again, right? So when you're getting lock, either, you'll start here, right? We'll go through here, we'll start checking headers. As soon as we see a bad header, we'll loop all the way around, we'll slip, we'll go back here, and we'll start checking at the next bit position. And we'll keep doing that until we see 64 good ones, and then we're done. Okay, once it's locked, then the behavior changes a little bit. If we see an invalid sync header, this is most likely because we got like a single bit error. So we'll keep track of how many invalid ones that we've seen. If we see 16 before we've seen 64 sync headers in total, then we'll say, oops, there's a problem. We're going to remove the block lock indication and restart the process of acquiring the block lock. If we haven't seen 64 yet, then we'll loop around here and we'll keep checking. So you'll be checking, you'll get one bad one, check, you get another bad one. If you get to 64 and you saw some bad ones, then you just reset the counters and you try again. If you hit 16 bad ones, then you reset and you clear out the block lock status and you start shifting until you get a lock again. So that's how it works. It's pretty simple. It doesn't take a lot of logic resources, but it takes some time to lock, right? Because you have to see a fair number of these symbols before you'll say that the lock is good, and it usually takes some time to actually implement the bit slip on the transceivers. On the Xilinx ones, it's pretty fast because of the connection is direct. So I think it's like 8 clock cycles or something like that is a reasonable number for how long it takes to do each bit slip. But on some of the Intel devices, the bit slip is actually done on the it's done on the other side of EMIB on the tile. So as a result, it takes a long time to do the bit slip, like 100 nanoseconds or something like that for each bit slip. I actually can't remember what the numbers off the top of my head, but it takes many clock cycles, and as a result, it takes a lot longer to get block lock. But this is in general pretty simple because they're just trying to lock onto a 66-bit frame. When you have FEC involved, it's a different story. All right, so this is already implemented, and we can certainly look at this to get an idea of what's going on, right? If we've been bit slipping for ages and ages and ages, then maybe we need to reset the transceiver. There's another algorithm as well that can potentially be useful. This one is kind of monitoring the BER level of the link by looking for bad sync headers. And if it sees enough bad sync headers in a certain amount of time, then it sets an indication saying that we're seeing a lot of bit errors on the link. Right, so this is doing the same kind of thing, except it's using a 125 microsecond timer to count up the number of bit errors. If we see 16 bad sync headers within that time, then you set high BER to true. Otherwise, let's see. Okay, so this has no bearing on the timer. If we see 16 errors, then we immediately set it to true and reset the timer. Otherwise, if the timer expires and we haven't seen 16 errors, then we set that to false. So yeah, that's pretty straightforward. I'm just looking at this. This seems like kind of the diagrams in here are not particularly good. This one is saying if the sync header is not valid, we go here. Oh, I guess you just stay in this state. Okay, gotcha. So if it's not valid, bang, we go here. If it is valid and the timer is done, then we go here. Okay. Okay, so both these are implemented, and we can use those pieces of information for determination as to whether the transceiver is operating correctly. But I think the main thing that we're going to look at today is not so much the sync header, but everything else. Right, so going back to the Verilog code, we have the base R decoder here, and I think we're going to have to add some functionality to the base R decoder to look at some of these other fields in a little bit more detail. This module, I don't think we're going to have to make any modification to. Let's just take a look very briefly at what is inside of each of these modules. So this one, the receive interface module, it brings in the SerDes RX data and it generates the encoded RX data. So the SerDes RX data, it has a potential bit reverse section, and then it has a pipeline section where you can add pipeline registers for timing. And then it has the LFSRs for, oh, this is for PRBS31, right? So it has an LFSR module for actually doing the descrambling. So the data comes in here, the descrambled data goes out there. And then that, let's see, what happens after that? I think that just gets passed straight out. Oh, I think it gets registered maybe? Encoded RX data. Okay, so depending on whether the scrambler is enabled or not, it either passes the data straight through, bypassing the scrambler, or it returns the descrambled data. Right, okay, and then that gets handed off. And then there are the frame sync and BER monitor modules. So the frame sync module implements this thing, and the BER monitor module implements this thing. Relatively straightforward. All right, and then we have the actual base R decode module. So this one accepts the encoded data from the interface module after descrambling, and this generates XVMI data, which will be handed off to the Mac. So what we need to do here is take a look at how to generate some more comprehensive status information. So this does several things. Let me actually, okay. So this does several things. Hang on a second. That's not great. I'm going to switch to a different microphone here for a moment. Okay, there we go. All right, so what we're doing here is several things. There are two different components to this. The first one is the mapping of the control characters from inside of the frames, inside of the 66-bit frames. All right, let me pull up that magical table again real quick. Okay. So what this first block is doing is it's taking all of these control characters. And these control characters always fall in exactly the same position. So the first one in, you know, the C0 is always here, C1 is always here, so on and so forth. So all of these guys are peeled off and remapped over into what the XVMI control characters are. And XVMI characters are, you know, indicated here. So we have LPI, we have we don't have start. We have LPI, error, we have the reserve control characters, and then we have the signal and sequence ones are not going to be handled here. Right. So there we go. We have idle, we have error, and we have the reserved ones, and that's it. And if we see something else, then we set this decode error signal here. I think I added this signal, but I don't think this is actually used anywhere right now. Yeah, it's not. Okay, so that's one of the signals that we can use. All right, so that's the first piece. This is looking at the control characters and remapping those. The second piece here is then looking at the sync header and the block type field. Right, so the first thing we do is we look at the sync header field and we see, okay, are we looking at data or are we looking at control? Right, so if we have data, then we just pass through the data. Otherwise, if we have control, then we have to look at the block type field. Oh, and actually, I guess one thing that I was going to do before I go into the Verilog too much is take a look again at this, at what's coming out of the PHY on the actual FPGA. Unfortunately, I don't think I can make this a lot bigger, but this is showing what the ILA has captured from a couple of different points in the design. So this is showing, let's see, the RX data here. This is, let's see, so the RX data is what's coming out of the serializer here, basically. Right, so that's one. And then we have the encoded data, right? So the encoded data is what's coming out here. And then the last one is the XVMI data here, right? So those are the three. 1, 2, 3, and then I have a couple of other signals as well. So if you look at the RX data, this is what's coming directly out of the transceiver, and this is just you know, a load of crap. There's you can't make any sense of that because it's scrambled with that linear feedback shift register. Right. But after the descrambling, okay, well, this is what's actually there, right? Block type 1E, all zeros, and the RX header is 1. Right. And then once it goes through the XVMI decode module, then you get this. You see all 7s, so all idles, and you know the RXC is set to FF. Simple. There's actually a couple other things we can look at here. Let me think. We can actually take a look at how this thing locks, right? So I'm going to put 2 windows in here. Okay, and now I'm going to replug the cable on the FPGA, and we're going to watch it lock. Okay, so I unplug it. Okay, and then I hit go, and then I plug that in. Oh, and I also have the trigger set to look at a rising edge on the RX block lock. Oh, that only ran once. Okay, cool. So I will stop that. Okay, there we go. So let's take a look at this here real quick. If I zoom in, we can see down here, I'm looking at the RX bad block and RX block lock and the RX gearbox slip. So the gearbox slip is a signal that goes to the transceiver and requests it to move to the next bit position. And you can do the same thing in fabric logic if you want with a gigantic barrel shifter that takes up a huge amount of logic resources, but it's easier and simpler just to request that the transceiver scoot over by 1 bit. Right, so that's the gearbox slip. So the trigger here is set on block lock. So when block lock goes high, that's when the ILA is triggered. If we look at the data coming out here, it's not idles, but we can look at, this is block type 5.5, right? So if I pull up our fancy table here, block type 5.5 is 2 ordered sets. And then we can see this is, well, 000002. And I think there's a mention of that in the XVMI section here. Link fault signaling, there we go. Sequence 000002 is a remote fault. So the NIC is reporting remote fault, probably because its receive side hasn't come up yet. All right, so that's that. But what we can see here is the bit slipping that's leading up to this while the PHY is trying to find the correct alignment. So what we can do is actually take a look at the data coming out of the serializer, and we can actually see the bit shifting taking place, right? So here's your sync header, and it's being shifted and shifted and shifted and shifted and shifted, and eventually it gets down to the bottom where it ends up getting moved over into the GTRX header. At that point, you have the correct alignment, and it locks. So yeah, there you go. That's what it looks like while the block lock routine is running and it's trying to lock onto the data. Before that happens, the RX data is just a bunch, or the descrambled data is just a bunch of crap, basically, because the descrambling is not doing what it's supposed to do until things are aligned. Once it is aligned, then this will extract the data properly. All right, so that's showing, you know, what's going on at the PHY layer. All right, in the actual hardware. Okay, so let's take a look at the Verilog again here. And let's see what we can add to this to try to make it a little bit more useful. All right, so where was I before? We have this block that decodes the control characters, and then this is looking at the block type field, and then after that we're looking, or sorry, this one is looking at the sync header, and then after that we're looking at the block type field. So all the different block types have a location in here, right? So we've got all the terminations. We got ordered set start in lane 0, start in lane 4, ordered set with start, 2 ordered sets, ordered start or ordered set in lane 4, and all control. So all of those various block types are in here. And then down here we have invalid block type. So you'll notice I had the bad block on the trace from the ILA. This is the only place where that's set. So what I want to do, let's see here. We've got the bad block indication. I think the next step is to add some method of looking at the, well, let's see, what do I have? What were the things we're going to look at, right? So one of them is looking for invalid sync headers. Well, we're already kind of doing that, or we already have a way of doing that. Data headers. If we see too many of those sequential, well, we can do that. Check the block type. Well, we're already doing that. Checking the control encodings, and checking for start terminate within or outside of packets. All right, so let's see, checking the control encodings. That's done here, but we're not doing anything with this decode error output. So what we need to do is generate a control character error signal, basically, using this based on how many of these input control characters are actually used. So in this case, when you're forwarding all of the control characters, then you would use all of these. But if you're sending all data, then you would ignore the decode error because they're probably all going to be set, right? For some of these other ones, same kind of thing, right? So this one, you're sending 4 control characters. This one, again, 4 control characters. This one, none. So yeah, I think the simplest thing to do, well, I can always refactor this later. So let's start out with something simple. So what we can do is take bad block, and every time we have control characters, well, I will go ahead, I will set this to 0 here. I will set it to 0 here. Oh wait, no. So this one, what we want to do is we want to check to see if we have any decode errors, right? So if there's any decode errors, oops, if that's not equal to 0, right? So this will say if we have any decode errors, then it's a bad block. In this case, there's only 4 control characters here. So what we can do is look at 3 to 0, right? Yeah, I think that's right. Yeah. Okay, so if any of these don't decode correctly, then you report an error. All right, so that's that. Here's another one. This is, again, this has 3 control characters here. This one has none. This one has none. Yes, OS. All right, that's 2 of those. Start in lane 0, ordered set. Okay, now we get into the termination control characters. This one has none. This one just has 7. So I can do 7. Right. Okay, there's 7, and then we have 7 to 6. And this one's to 5. Right, so we can just mask these off. So that's 3, and that's 2. And this one will be to 1. And then I'm going to go ahead and make sure all these other ones get set to 0. Oops, I don't want that one. That one, all right. Because this one has no control characters, right? This one also has no control characters. This one does not as well. Wait, this one has 4. All right, so this one I need to do 7 through 4. Okay. And then I think there was there one more? I think there was one more. I think there's one more I need to set to 7. I think that's with all, yeah, terminate in lane 0. All right, so now every single one of these is setting the bad block indication based on the, not just the block type field, but also the control character encodings. All right. So the next thing we can do is generate, I'm going to call this, how about a sequence error? And the idea with this is we're going to look at whether or not we're within a frame. And if we see something that we're not supposed to see in a frame or outside of a frame, then we'll generate a sequence error. So let's call this sequence error. Okay. And the bad block, where was I setting that from? Okay. All right, and then I also need a frame indication here. Okay, so that one we're going to use to determine whether or not, or to keep track of whether we're in the middle of a frame. All right, and that's going to be set to the reg. All right, and then I need both of these guys. Like that, and then frame next equals frame reg. All right, and then down at the bottom, I need to go ahead and add these guys as well. All right, there we go. So this is pretty straightforward. For the frame reg, we're going to set that when we see a start control character, and we're going to clear it when we see a termination control character. So there's a start in lane 4, right? Frame next is set to 1. Okay, here's another start control character. Another start control character. Okay, so there should be 3 of those, right? Start, start, start. Okay. And then all the terminates, we're going to set this back to 0. All right, there's 1, 2, 3, 4, 5, 6, 7, 8, because we can terminate in all of the various lanes. And let's see, I guess the other thing that I should do as well is that you're not really allowed to send control characters in frames. Although I guess that doesn't really terminate a frame, does it? If you send an error. So this is one slight, maybe annoyance, I guess you could say, between XVMI and the 6466 encoding. Because for XVMI, let's go take a look at that section again really quick. For XVMI, you can just stick an error control character in the middle of a packet and say, yeah, there was an error there. And this encoding is allowed. But you actually cannot encode that with 6466 encoding for 10G base R, right? I mean, if we look at this, how would you encode that, right? We want to stick a random error control character in the middle of data, right? I mean, you can't do that. There is no encoding for that. So you're not going to get a random error marked in the middle of a frame. I think what will end up happening is you'll have to send, block type 1E with all errors or something along those lines, which kind of smears it out a little bit. To be honest, I don't think it makes that much difference if we're only resetting the frame indication with terminations or if we reset it with any control characters. So I think I'm just going to leave it for just terminations for now, and if it's any other control character, then we're just not going to change that state. Obviously, you don't change it. Obviously, you don't change it for data. Okay. So that's step 1. Step 2 now is how do we generate the sequence errors? All right, so if we see a start, but we're in a frame, this is going to be, so if we see a start control character, but we're in a frame, then we report a frame error, right? If we're not in a frame, then it's not an error. All right, so that's pretty straightforward. We're going to go ahead and add that to everything with a start, and then everything with a terminate, we get the exact opposite. If we're in a frame, then it's fine. If we're not in a frame, then it's an error. All right, then we can take a look at what this looks like in simulation. I've been thinking about porting this over to, porting the test benches that I had for the PHY over and putting them in the Coco TBX PCIe, or not PCIe, but Coco TBX Ethernet. But I wanted to come up with a, kind of long-term, more flexible way of doing that. So last night I went ahead and ported the test benches over to Coco TB, but just using an internal model that's just in this repository. So that'll work well enough for the time being, and allow us to test some of this stuff. Okay, so now that we have this wired up, let's see what happens if we run this in simulation. So I have a test bench here for, let's see, where did that go? I want the XVMI base R decoder. There we go, this one. All right, so I'm going to go ahead and run that. Come on. All right. We'll run that and we'll see what this does. This should run. It shouldn't error out, assuming I don't have any syntax errors. But we'll have to see what it looks like in terms of the trace. Oh, actually, I need to do this again. Make clean. I need to make it with waves. All right. While that's running, there we go. There's a waveform dump. I'll open that up in a moment once this is finished running. Okay, there we go. That's done. Let's take a look at whether these signals are doing what they're supposed to do. All right. We'll take a look at that. And where's frame reg? Okay, so frame reg, I'm seeing. Oh, I guess this is fine. Yeah, it's dropping down between the frames. Yeah, so this looks okay, right? So for each frame that's being sent, well, let's take a look, right? We have the XVMI data down here. We have starter frame through the, well, all right, so start control character, there's a starter frame delimiter, and then we have the actual frame data. And then at the end, there's your terminate, and why is there an FE? Not sure why there's an FE there. All right, so that is, so the encoded RX data, that's 8.7. Not sure what's going on with that. 8.7 is, okay, yeah, 8.7 is going to be terminate in lane 0. All right, 8.7 is terminate in lane 0. That makes sense. 87038. All right, that's terminate in lane 0. But why is this? Why does this have a 3.8 here? That's got to be a bug in my my model then. So that should generate. That generates a bad block indication. All right, I got to take a look at my model. I have a mistake here in terms of how that one is being generated. Let's see. So this is. What is going on here? Oh, is that? No. So this is going to be, this is the source, right? This is the source, yes. So the source is going to be generating this based off of XVMI controlled base R mapping. This is coming off of, yeah, the XVMI control characters going in. Was the problem the frame wasn't long enough? If there's a... Oh, maybe that's what it is. Alright, well, I'll have to debug that later. That's not a big deal. But that does indicate that the bad block indication is now working, because this had a decode error. Let's see. There's the decoded control, decode error, yeah. So the highest one had an issue with the decoding, right? Because this 8.3 is not valid. That is a test bench problem that I will have to take a look at. So that indicated a decode error, and that was passed through because that control character was used. And yeah, okay. Well, I would expect that to be low the whole time, but all right. Test bench problem, I will sort that out later. But the frame does appear to be working correctly. What I'm not seeing are any sequence errors, and I don't think there's a way to test that easily with the way this test bench is set up right now. Yeah, but that's fine. That's fine. All right, so that seems to work. Now what we need to do is put together the kind of higher level component, the actual Watchdog. So there's two components to this, right? The first one is looking at all of these various aspects of the input of whatever's coming out of the SerDes, right? The 64, 66 blocks, checking to make sure all of the encodings are correct and whatnot, checking to make sure that we're seeing the sync headers that we want to see. The next piece of this is actually collecting all of this information and generating the reset signal that's going to cause the PHY to reset itself. All right, so what we're going to do is go into, it's going to be the RxIF, or is this going to go into the Rx module? I don't think it makes that much difference. Probably the RxIF. All right, so Rx sequence error. We have another connection here, Rx sequence error. I need to add that to the top level as well, Rx sequence error. All right, and then both of these are going to be passed in to the RxIF, so this information can be shared. All right, so the RxIF, that sees the sync headers already, and all we're doing now is passing through these indications from the decode module. All right, so this goes into the RxIF. Yeah, all right, so these are going to be inputs here. All right, Rx bad block, Rx sequence error. Okay, so these two get duplicated here. All right, cool. So now we're taking these status signals out of the decode module, and we're passing them into this IF module. And there's one other connection I need as well. This is going to be SerDes reset request. I guess I should move that up here. Rx reset request. Okay, there we go. All right, so this is the signal that we're going to generate. Let's see, I need to connect that. That goes here, Rx bit slip, and that goes here. Oops. All right, there we go. So now what we need to do is create another little module. This is going to be PHY 10G Rx Watchdog. All right, cool. So this one is going to monitor all the status information that we have, and based off of that, it will issue requests to reset the transceiver. All right, so what information do I need here? going to make a copy of one of these for the time being, and then we will modify it here. Right, so this is 10G Ethernet PHY. The Watchdog, assuming I can type. RX. All right, there we go. Header width 2. I will leave those out for now. All right, serdes interface. So we are going to have the RX header. Let's see, what did I add to this previously here? I'm gonna add this guy here. Right, so the serdes RX reset request, and then I need to bring in the status signals. Oh, I don't have that. Okay, there we go. So let's see then. This is going to be bringing in, where did I add those again? That was here? No, that was here. That is here. All right, so I need to look at bad block, sequence error. And I guess I can also look at block lock and high BER. All right. So I will go ahead and bring these in here. All right, so that goes away. So I have high BER, block lock, RX sequence error, and RX bad block. All right, that looks pretty reasonable. All right, let's go ahead and remove stuff that I don't need here. Oh, and these are all inputs. Yes. Inputs, yes. Okay. Great. And I'm going to go ahead and add these now to, well, I will take this module, and this is going to be added as an instance at the bottom of this guy here. All right, so I do that. Okay, and then this is FPGA RX Watchdog inst. All right. Then we have, most of these are going to be wired up same way as these guys are. All right, so there's that, and then this is going to be the reset request. Reset request. Okay, that's the output, and then the monitor connections, these are going to be wired up as is. All right. Okay, there we go. So this has, I believe, all of the connections it needs. So I'll go ahead and save that. And then we'll go over here. And I'm going to go ahead and comment out all of this for the time being. And let's make sure that I can run the PHY test bench. I need to go ahead and add the files. Adding a new file means you need to make an edit here. This is going to be the RX Watchdog, right? And I got to do this again over here. RX Watchdog. All right. So now I should be able to run the test here. We'll make sure that runs correctly. I also have the waves pulled up over here, which we can take a look at to make sure that this is doing what it's supposed to do and all of the correct connections are there. All right, there we go. Test bench is finished. So we'll take a look at this. Let's see, where is this module going to be? This is the RX IF, and I think that is the Watchdog. Yes, all right. So I'll go ahead and refresh this. That looks fine. Okay. So there we go. In the Watchdog, we can see all of the signals that I've connected. That output signal is not driven yet, so that's fine. Wait, why are we getting an X on the sequence error? Let me take a look at that. That doesn't make sense. All right, so that's going to be computed in the decode module. Okay. I get an X because the frame was an X. All right, let me go ahead and add a reset then for that. That was in the decode module here. I have a reset connection, I'm just not using it for anything right now. Okay, so if RST, then I can do frame reg. I will set that back to 0. Let's run that again and see if that solves this X. Fortunately, this test bench doesn't take all that long to run. Okay, there we go. There we go. That's better. All right. So now from the standpoint of the Watchdog, I shouldn't get an X there. There we go. That's more like it. All right. Perfect. Okay. Now let's actually implement the all the time-based functionality here. So I'm going to need, as usual, a couple of different always blocks here. This one is for the sequential portion. This one is for the combinatorial portion. All right. So let's think about this, right? There's a couple of different things that we need to look at. The first one is we need to look at the number of invalid sync headers that we're seeing. And if we see a whole bunch of invalid sync headers, then we need to do something about that. Let's see here. I think these conditions are going to come kind of in order of priority, right? So if we are seeing invalid sync headers, then all of the other signals should be ignored because they're not going to be reliable, right? If you're seeing invalid sync headers, then that means we don't have lock. Actually, I guess we don't need to look at sync headers necessarily, right? We could look at block lock. If we haven't seen block lock for a very long time, then we reset the transceiver. If we do have block lock, then we can look at the other signals, right? So if we have RX block lock, then we do something. If we don't have block lock, then we do something else. All right. So I'm thinking that the Watchdog kind of needs to be divided up into a couple of pieces to try and reduce the number of false positives while making sure that we can capture whenever the transceiver is doing something weird. And I think the way to do this is to have kind of a first pass that looks at numbers of various events that have occurred over a certain time period, and then the second one make sure that we see continuous problems over an extended time before we reset the transceiver, because we don't want to reset the transceiver when we see a couple of bit errors. We get bit errors. There's not much we can do about that. We only want to reset the transceiver when something is actually totally wedged and totally screwed up. So let me think about this for a second. The high BER component, that is looking at a 125 microsecond counter. So potentially what we can do is have this second order kind of computation do something on a similar time scale. So 100 microseconds or so, if we see problems, then we set a flag, and then if we see problems in several 125 microsecond time periods, then we reset the transceiver. I think that makes a fair amount of sense. So I'm actually going to go ahead and copy over. I did not remove the parameters. Yeah, okay, so I'm actually going to bring this parameter back. I guess I copied the other one. Yeah, okay. So I can use the same counter here. count width, I can compute that. Let's see here. Okay, so I can have a register here to keep track of time. Okay, cool. And how did I use it here? All right, so the time count, that hits 0, then the 125 microsecond counter has expired, and the idea is I just subtract 1 every cycle. And then this will sit at 0. Okay, so I can do something similar. Well, I guess my thought is I'm not going to play around with this, I'm just going to let it run. All right, that's fine. All right, so if time count reg is greater than 0, then I subtract 1. Otherwise, I set this equal to, what was this here? And I think I usually do -1, right? Oh, okay, that's fine. All right, so now I need to go ahead and add the time count reg down here. All right. Okay, and I can go ahead and reset that to that. All right. I'm just realizing that this was kind of a weird way of doing that. So if this is reset to 125, but it starts out as 0, that's not so great. Okay, let's change that. And let me just check to make sure that doesn't break anything in my PHY test pitch. I think that'll run fine, but okay. All right, so when this thing overflows, then we're going to do some stuff. Cool. All right, so let's think. What are all the things that we're looking at, right? We're looking at maximum packet sizes. So let's think about this for a second here, right? So if we have 125 microseconds, how many cycles do we have in 125 microseconds? 125 microseconds, 5e minus 6, right? And the clock period that we have is 6.4 to the -9. So we do this over, we get about 20,000 clock cycles. All right, and we can transfer 8 bytes in each one of those. So that is 156 kilobytes worth of data. That actually works out pretty well, right? So if we see data sync headers the entire time, and we never see a control sync header, then that's a pretty good indication that that something is not good, right? That's a reasonable amount of data, I think, right? That you're not going to be getting anywhere near that with any normal MTU size. And in fact, I think even for things like IP, the payload size field is 16 bits, so you can't even send anything larger than, you know, 65 kilobytes or 64 kilobytes. Right, okay. So let's see. What we can do in this case, if we have RX block lock, is we can check to see if we have anything other than data in the headers. Right, okay. So we got serdes RX header, we have the header values here. So if this is equal to control, so if we see a control header, then I need to add a flag here indicating that it's not all data, basically. Okay, what should I call that? What are all the hard things in computer science, right? Caching, cache invalidation, naming things, and off by 1 errors. Yeah, okay. So I can just call this all data. And then what we can do is clear this. Right. Okay, so there we go. And when we reset the counters here, then I will set this back to 1. All right, cool. So we have the all data reg here. That's all data next, and the same thing here. Okay, great. So that one will be set initially, and then as soon as we see a sync character or a control sync character, then we will set that back to 0. All right. And what we're going to do here eventually is look at all these flags, and if we see a problem, then we'll increment an error count. All right, so let's go ahead and create that. We'll make it about 4 bits wide, sure. All right, cool. So the idea here is we can, oh, I need to do a couple of other things here. Right, all data next, all data reg, okay. And then I also need to do, that equals error count reg. All right, and then what we're gonna do here is if all data next, okay, then we will set error count next, error count reg plus 1. Okay, so there we go. That's pretty simple. If the block is locked, if we have block lock, right, and sync control is, or if we have block lock, right, and we are seeing control sync headers, right, then we clear this. If it's set, then we increment the error count. Okay. And then we go ahead and reset that flag. Actually, I guess the other thing I should do too is if we don't have block lock, then I will also clear that flag. Because it's not going to be all data in that instance. Oh, actually reset, that needs to be, okay. And then I also need the error count. Okay, one more of these here. Okay, there we go. So this increments the error count. Now, if none of these are set, then what I will do is set this to 0. And then if the error count reg hits a certain level, then what we can do is issue a transceiver reset. Right, so that's another thing I need here. This is a serdes RX reset request. So I need another one here, reg. And oops, next, okay. Okay, there we go. So there is that reset request. So now if error count next equals, let's see here. So if this equals, okay, I'm going to do, if all the bits are set, then we can set, we'll set that high. Okay, that will request a reset of the transceiver. And then actually, I'm not going to put that, I'm going to do that. So there we go. We'll set that like that, and then I'm going to go ahead and add this down here, and add this down here as well. Okay, cool. Let me get rid of a lot of this stuff that I've commented out that's just taking up space. Let's get rid of that. All right. A little bit easier to read now. Okay, All right, there we go. So let's follow through this logic again. If we don't have block lock, then we clear this flag. If we have block lock and we see a sync control header, then we clear that flag. So if we have block lock and we're only getting data, then that flag stays set. After 125 microseconds, then this piece runs. If that flag is set, then we increment the number of errors that we've seen, right? If that flag is not set, then we set this to 0. If the error count reaches the maximum value, right, if it's all set, then we go ahead and issue a reset request on the transceiver. So this should reset the transceiver, and then at this point we reset all the flags. So we set this flag back to 1, that this one will then clear. Okay, pretty straightforward. All right, let me make sure that so far the test bench runs, right? We don't have any syntax errors. Okay, it's running. All right, that's good. Okay, so that is the data. That's looking at the sync headers to look for long sections of data. All right, cool. What else can we do then? I guess another thing that we can do is if we haven't seen block lock, if we haven't seen block lock at all, then we do the same thing, right? If we haven't seen block lock, we're going to do the same thing. All right, if we see block lock for, well, what's going to make the most sense? I think with block lock, it's possible you'll get, false block lock indications periodically just due to noisy stuff. So it may not make sense to look for the same thing, right? To look for block lock being set continuously. But what might make more sense is to have like a counter. And if block lock has been clear for more than a certain amount of time, then we will count that. I guess what we can do is just count block lock being low at all. If it's low at all for 16 of these little sampling periods, then we can use that to reset the transceiver. Does that make sense? The issue is I'm also thinking about some of the research that we're going to be doing, and potentially we're going to be breaking the links every 100 microseconds or so, and that is going to cause block lock to go high, or to go low. So I think that condition is going to be a little bit too extreme. Well, so to get block lock set, you have to see 64 sequential blocks. So I think it's going to be pretty hard to set block lock or to set block lock at all. Well, but if you set block lock and you're getting garbage, then the idea is that all of the other conditions that we have are going to, help solve the problem. Okay, that should be fine then. All right, so what I'm going to do, let me go ahead and refresh this here. That requested, why was that set there? Error count next is 0. Oh, because I reset it to 1. Why did I reset it to 1? Yeah, all right. All right, well, that's okay. Let's see, so all data that initially is set, but it's cleared immediately because we're seeing control characters. Cool, and the time count reg, this is going to be slowly counting down, I would think, right? Yeah, all right, that looks good. Let me go ahead and zoom out. Oh, all right, so I don't have that connected in the parent module because if I wire this up, then for simulation, I use a different value of that counter. All right, let's run that again, make sure that looks good. Okay, so what I'm going to do in this case is the same, oops, this module. I'm going to do the same thing I did for the data, right? If block lock ever goes, let's see, what we're looking for is block lock low the entire time. If the block lock is low continuously, then that means we might want to reset the transceiver. If block lock goes high, then we can look at some of the other parameters. All right, so reg, let's see. I'm going to say all right, and block locked next. Okay, cool. So we'll take that. This one will come here. Same thing. All data reg. Yeah, all right. And then this one, same thing here. Okay, cool. All right, so if we see block locked, then we will set that high. All right, and then at this point, I will go ahead and, oops, I don't want to do that. And there's a B there. All right, there we go. All right, cool. And I can just start adding these here, or not saw block locked. So if I didn't see block locked, then I increment the error count. All right, that looks better. All right, let's run this again. So what we can do is just build up all of these various conditions, and from that, what we can do is reset the transceiver. And I'm going to build this in a few minutes. We'll put it on the board and we'll see if things are a little bit better behaved. All right, so it's running. All right, there we go. Test bench is done. Okay. Yeah, all right, so now the timer is cycling much more frequently. There we go. So we can see the all data getting set. In this case, this was set for a while because that was moving a large frame, a jumbo frame, and because the timer count is very, very short right now. Okay, so what we should be seeing, if all data is set, no, this should be getting incremented. It isn't. Why is that happening? All data next, right? Then we should set error count next to error count reg +1. That should be happening every time counter rolls over. Right, so that's the saw block locked. That's interesting. All right, so saw block locked is getting set back to 0, but the error count is not being incremented. Oh, wow. All right, I've forgotten else. I actually did not realize that isn't a syntax error. So you can actually apparently put a begin and end block just kind of randomly in the Verilog. I don't know how useful that is, but okay. All right, it's almost done. All right, running the last test. There we go. All right, there we go. Now we can see that the error count is now incrementing. 1, 2, 3, 4, 5. Right, and then it hit the end of the packet, so it reset the error count. All right, excellent. So let's see. Of all of the conditions we were thinking about before, we're looking at the sync headers to look for long packets now. We're looking at the block lock to see if we're not seeing that. Let's see. What else was I thinking of? Let's take a look at this table again here. Right, so sync headers, data headers, too many. Checking the block type, checking the encodings, and checking for the start terminate within or outside of packets. All right, so for that, what we can do is have a packet error count. I need one more register here, right? Register. I'll do the same. Well, I'll make this a little bit bigger. No, I'll start with 16. I can make it bigger later. So this is block error count. Count reg, set that to 0, and then I need another one of these. Next, all right, there we go. And what we can do here is put this guy here. All right, so this is Okay, all right, and this goes here as well. I need to set this to 0. All right, so what we're going to do with this guy is if we see either RX bad block or RX sequence error, I will increment this guy. All right. And one more thing, I want to saturate this. So I can add saturation logic here. So if that's not all ones, then we'll increment it. Okay, cool. And now what I can do here, I need to do two things, right? Down here, I'm going to set this to 0. And in this case, I'm looking to see if it's all set. So if that's all set, if I have a bunch of errors, then I will count that. All right, cool. This is actually, I think, almost done. And then we'll be able to test that. Oops. Syntax error. Something is more pedantic than I expected. All right. Is that going to work? Okay, there we go. Okay, actually, I guess there's a couple of other things that I need to do. Now that I have the reset request output, what I need to do is attach it in the design, right? So in this case, I'm looking at, well, let's see. So I have this in the IF. Did I pull this all the way up to the top of the PHY? No, I didn't actually. I need to add a couple more connections here, right? So this one I have, need to add sequence error output to the top level PHY, right? Bad block and sequence error. And then I also need to add the reset request output. And both of these need to be connected to the RX side here. All right, so we have bad block, and this one is going to be sequence error, and then I need to do one more of these here. This is going to be the RX reset request. All right, there we go. Now that signal has been brought out through the top of the PHY, the next step is to connect it to the transceiver on the FPGA. Let me take a look. Did this finish? It did finish. Oh, I don't have that was a new register, so it's not there. Here we go. We can see the block error count incrementing. It gets up to C and then it resets. Okay, well, this is an aspect of my test bench, so whatever, that's not really a big deal. I'll deal with these bad block indications later, but this actually is a halfway decent test. Right, so the error count regs, yeah, so we never implement the error count reg except at this point. All right, well, that actually seems to work. Okay, so we can also see that the error count reg is incrementing while we have the block lock deasserted. So block lock's deasserted, increments, and eventually that would lead to a transceiver reset if it didn't end up asserting at this point. Okay. Cool. So we'll have to take a look at this and see how it works. All right. So that's looking pretty good. Let me go ahead and take a look at the actual code here for what we're running on this FPGA. So this is the Xenix X25. I need to add, again, the reset request connection and the sequence error. All right. So here are the PHY instances. I'm going to go ahead and add this here, reset request. And one more here, reset request here for this guy. Okay, reset request, and then I need to add the sequence error as well. Is that how I had that, sequence error? Yeah, all right, cool, so I have that. Okay, and I'm going to make this RX reset request. Okay, so I have that one. That's SFP2. All right, cool. And then the sequence error that goes right after bad block. Again, SFP2. All right. Now I need to add those as well. So I have the PMA reset lines here. Where did I have the bad blocks? Here we go. So I have bad block, and I also need sequence error for both of these here. Oops. Okay, there's the sequence errors. And then the other thing I needed was the reset request. So that's going to be on SFP2. All right, cool. So there are the reset request connections and the sequence error connections. Over here, I have the PMA reset connections that I brought out on the GTY instance. So now what I need to do is wire up these PMA reset connections with the signals coming out of the PHY modules. All right, a couple of things that I'm going to do here then. Okay, so this is the ILA instance and the VIO instance that I have. So what I'm going to do is add so the gearbox slip. Then I have the SFP1 GT. Oh, SFP1. Heh. GT PMA reset. Okay, cool. And I have bad block, block lock, and also sequence error. Sequence error, bad block, block lock, and SFP1 RX sequence error. SFP2 RX sequence error. All right, those are the PMA resets. So I'm going to create another one here for the PMA resets for the VIO. I need to rename these guys, yeah, so I don't have a conflict. All right, and then what I'm going to do is assign SFP1 GT PMA reset. This is going to be SFP1 GT PMA reset VIO or SFP1 RX reset request. Okay, and then I do this for SFP2. And there we go. All right. Now I need to go over to Vivado, which I have over here. And I need to add this new file to the project and rebuild it, which will take a couple of minutes, but shouldn't be that bad. Let me make sure we got this. Okay, yep, there we go. I now need to add this guy here, add sources, add or create design sources, right? So this is going to be, let's see, lib eth RTL, eth by 10G. Where is that one? Oh, that's eth Mac. Watchdog. There we go. All right, cool. Finish. I'm gonna pick up the file. There we go. All right. Vivado being slow as usual. All right, so at this point, I'm going to go ahead and hit build, and we'll see what happens. This will take a couple of minutes, but once that's done, then we'll load it on the FPGA and see if things are behaved a little bit better. All right, if anybody has any questions about anything, feel free to pop them in the chat. This will take a couple of minutes to complete. I'll go ahead and pull up the log here so we can see exactly what's going on. Let's see, is there anything? Let's do, this is one thing I like doing. Whenever Vivado is running, I like just going over the code to make sure everything looks reasonable. All right, so what are we checking now, right? We implemented several things in the Watchdog. Let me go find the Watchdog code again. Where was it? Here's the Watchdog. Okay, so several things, right? If we have block lock, let's see here. Yeah, so all the other ones shouldn't be set. Yeah, so if we have block lock, then this one will be set. If we don't have block lock, then this one will be clear, but everything else will be left alone. Okay. If we have block lock, then we will look at the sync headers. If we see all data, then this one will be set high. If we see any control, then that'll be set low. Let's see, if we see bad block or sequence error, and we haven't saturated, then we will increment the block error count. Once that saturates, or we haven't seen block lock, or we're getting all data, then we increment the error. Okay, if the error maxes out, then we go ahead and issue a reset request and roll the error count back around to 0. All right, seems reasonable to me. We'll have to see how this performs on the FPGA. All right, no errors so far coming out of Avado. All right, is there anything else we could check? I think there's a few things right now that we're not checking, potentially that we could check. Let me see here. Going back to the decoder here. I guess one thing that we could do. Yeah, so this is marking an XVMI error in place of invalid O codes. So if the O code is different, then we are reporting an XVMI error. But what I could do is actually check these fields as well, and in this case report bad block, which is, you know, not a difficult thing to do. So we'll do that. RX bad block next. I'll move this up here. Same kind of thing. Set that under that condition. I'm not going to rebuild this code now, but you know, this will be for later, right? So that's checking that, and I think I have one more encoding with an O code where I can shuffle that around to also check the encoding of that. Oh. Well, this one's slightly more complicated, right? Because, well, I guess not necessarily, right? I just need to move this here. And then move this here, right? So in this case, it is the correct O code, so we'll pass through any decode errors in the control characters. Otherwise, if the O code is wrong, then we will report a block error. All right, cool. Well, I can test that out later. Is there anything else we can check? I guess one thing I'm not checking is the state of any of these little gaps in here. I'm not sure if there's a required level to be sent in those, though. Multi-driven net. Uh-oh. That's a problem. Saw block locked next reg. Okay. That I need to fix. Saw block locked. All right, let me take a look at, oh. Oops, all right. This is why you look at the logs, right? Cancel the process, let's restart that. Okay, generate bitstream. Yep, do it. Okay, there we go. I guess this is why you use a linter. I need to set one of those up at some point. All right, since I restarted that, I might as well rerun the simulation and use this slightly better set of checks. All right, there we go. This is starting. All right, this will take a few minutes to run. Okay, so sync headers, right? We're checking that. Data, we're checking that if we see too many of those. Block field, we're checking that. Control characters, we're checking that. O codes, we're checking those now. and all of the control encodings, we're checking all of those. Yeah, so what gets set in these guys here? I'm actually not sure. I'm setting 0. I'm not sure if those are required to be 0 or not. I'm assuming they probably are. Valid and invalid blocks. Yeah, okay. A block is invalid if any of the following conditions exist. Sync field has a valid value of 0, 0, or 1, 1. Block type contains a reserved value. Block type, yeah, okay, that's fine. Any control character contains a value not in table 49.1. Yep, any O code contains a value. Or the O code F is received on an Ethernet PHY, that's fine. The set of XVMI characters does not have a corresponding block format in 47.9. Yeah, okay. Cool. I'm wondering about those gaps. Doesn't seem to say anything about those gaps. Yeah, not sure what the story is with that. Anyway, while this is running, I guess I can talk a little bit more about kind of the purpose of the line code that's used in, well, any kind of serial communication systems. So for 10 gigabit Ethernet, this is the standard, the 6466 line code. This is not the only line code that exists, right? For other protocols, there's a number of other formats that can be used. So one of the pretty common ones is something called 8B 10B. And it basically does the same thing as 6466, where it takes some number of input data bytes and it packs them into, longer code words. And PCI Express uses something called 128B 130B, same kind of thing. But as you can see, the ratio between these two numbers gets smaller and smaller. So 8B 10B, you're adding 2 extra bits for every byte. So the overhead is pretty high, right? It's like a 20% overhead or 25% overhead, right? This is where you get differences between like the reported data rate and the actual theoretically achievably data rate, or one source of that. So USB and PCI Express tend to report the raw link rate, which is after the line code. So for 8B 10B, that's like a pretty high overhead. So PCI Gen 1, for example, is 2.5 gigabits per second, but that's after the 8B 10B encoding. If you look at how much data you can actually send in terms of the 8-bit bytes, it ends up being 2 gigabits per second instead of 2.5 per lane. Same thing with USB 3 as well, right? It reports 5, but that's after the line code. Before the line code, it's only 4. So Ethernet, they specify actually the data rate before the line code. So it's 10 gigabits per second, but then after you add the line coding, what's actually running over the wire is 10.3125 gigabits per second, which is a little bit faster. And for gigabit Ethernet over fiber, that uses 8B 10B encoding, and in that case, the link actually runs at 1.25 gigabits per second. It's also the same thing for SGMII, which is a serial version of GMII that uses a single pair of wires. It's actually almost the same format as gigabit Ethernet over fiber. Anyway, there's a bunch of different line codes that are used, and they all serve kind of similar purposes. They all have slightly different characteristics. Mainly, the most obvious one is in terms of the overhead. So 6466, that's something like a 3% overhead. For 8B 10B, that's higher. For 128 130, as in PCI Express, it's lower. In fact, I think I have the PCI Express standard up here. Let's take a look at what the line code is in PCI Express. Let's see here. This is going to be in the physical layer. Well, this I think actually talks about both the 8B 10B and 128B 130B encoding. Yeah, so the other thing I should mention is that PCI Express also uses scrambling, but it does the scrambling in a completely different way than than Ethernet. So this is what the Scrambler looks like for PCI Express for 8B10B. So this is for Gen 1 and Gen 2. As you will notice, the data input doesn't go through the actual sequence computation. So basically what you're doing is you're taking the sequence, right? And then you're just XORing it with the data. Apparently with an 8-bit delay. I'm not sure what the story is with this delay exactly, but this is not a self-synchronizing scrambler. And I think they do that for, you know, the bit error reasons. So you're not getting multiple bits flipped because of the scrambling. But this does mean that you need to do more work to bring up the link, and that everything needs to be, you need to synchronize the scrambler state periodically. And in PCI Express, all the links are, you know, in system point to point, and there's a lot of negotiation that takes place between the devices at opposite ends of the link. So you can afford to do that. With Ethernet, the devices could be on opposite sides of the country, and you can't afford to, you know, do this kind of scrambler synchronization or whatnot, because you don't necessarily have a bidirectional link, or you could have a very high delay. So everything is set up in Ethernet to kind of loosely couple the transmitter and the receiver. Right, so does this talk about 8B10 very much? That's kind of a similar setup in terms of having, you know, various control characters for, you know, frame start and frame end and whatnot. I'm going to put this over here so I can keep track of it. Okay. Okay, so this talks very briefly about the 8B10B transmission code, right? You get 8 bits coming in, you do the encoding, you get 10 bits going out, and those get transferred over the link. So they don't actually say anything about the encoding, because they just say, hey, it's the same as this other specification. All right, cool. So that doesn't talk about it. But for the higher data rates, they use a different encoding scheme. And let me take a look at how this works. It's somewhat similar to 6466 in that they add a sync header onto a block of, you know, 8-bit symbols. You'll see that this one looks basically exactly the same as this one, right? They have the 2-bit sync header, and then they have, you know, 16 bits, or 16 bytes rather, instead of 8. I think they always send the same sync header. I don't think they have a differentiation between control and data sync headers here. Let me see if I can verify that. Okay, all right, now they do have 2, right? So 10 indicates a data block, 01 indicates an ordered set block. Each ordered set has a 128-bit payload, resulting in a block that's 130 bits. Okay, so the ordered sets are used to indicate specific things on the link, and they can be, you know, removed, inserted or removed kind of atomically. PCI Express uses a lot more of this kind of signaling than Ethernet does. For sending the actual data, they don't use this kind of out-of-band signaling the same way. They use these tags. So at the start of a packet, you'll have a token that is inserted before the packet, and this contains the length of the packet. And it also contains a CRC that protects these fields here, right? So the length here, that's 10 bits, and then the CRC protects these fields. So this is kind of a different setup from Ethernet, where Ethernet has a character that indicates the start of the frame and a character that indicates the end of the frame, and you can unambiguously detect those symbols and separate them out from the stream of data. For PCI Express, they just use a token at the start that says, here's how long the packet is going to be. So it's a very different way of doing things, because they don't actually have a token to indicate the end of a frame. They have EDS and EDB, and I'm trying to remember what these are for. I think EDB is end bad, Yeah, end bad and EDS end of data stream. So that indicates that the next block will be an ordered set block, right? So if you're going to send an ordered set, then you send one of those, and then you send the ordered set. Because Ethernet works differently, you don't need to use these tokens because it's less ambiguous. Oh, looks like Vivado is done with the synthesis. It's moving on to the implementation. All right, cool. There'd only be a couple of more minutes here. Let's see, it's doing post-placement timing analysis. All right, cool. There'd only be a couple more minutes before that's done. Right. So I've talked about a couple different kinds of line codes and a little bit how they're used in PCI Express and Ethernet, but what do you need a line code for? Line code provides several different features. One of them is it provides framing, right? It allows you to detect the byte boundaries, and this is very important in serial links. In parallel links, it's less important, right? Because bit 0 is always going to end up on bit 0, right? It's not going to suddenly get shifted over to some other wire. With serial links, since all the bits get sent down one wire, you have to have some way of figuring out where all the bytes are. So that's one thing that allows you to do. And you see this as well with like a UART, for example. You have start bits and stop bits. And it's the same idea there, right? You're sending the bits down the wire one at a time. You have to determine where's bit 0, where's bit 7, how do we get them in the right order? The start bit and the stop bit allows you to do that. So that's the same idea here. The other thing that this provides is the ability to send some small amount of out-of-band data, right? There is a split between the data symbols and the control symbols that you can send down the link. And this is extremely useful because you can use a small amount of control information to indicate, unambiguously the beginning and end of frames that are sent down the link. For something like a UART, there isn't really a nice way of doing that because the protocol doesn't really support sending out-of-band data. There's a couple of techniques that I've heard about. You could use like a break, right? You can hold the line in the active state for a while. You can do some timing related stuff. Not particularly all that great. You could send more bits, right? You could send 9 or 10 bits per symbol or something like that. That's a possibility. I'm not sure how good of an idea that is. That's not necessarily a standard thing, but that would allow you to mark some bytes. Another thing that you can do too is if you're using just the lower 7 bits for your data, you could use the 8th bit for framing if you wanted to, or you could use various encoding schemes. So there's something that I've used before called COBS, and with that, what you can do is it basically removes all the 0 bytes. It encodes the data that you're sending so it has no 0 bytes in it, and then you can use 0 bytes for framing. So, that there's a few things you can do by, layering some stuff on top of something like a normal serial link. But the other thing that line codes do is they give you some electrical characteristics as well. So whenever you have a high-speed signal, you're going to have to connect multiple components together, and when you do that, you have to deal with various electrical issues. So one of the things that's very common in some of these high-speed systems is you use DC coupled AC coupled connections. So you look at all these little capacitors here that are sitting in the PCI Express link, the Zowie connections on like this Miracom NIC, same kind of thing here. All of these DC blocking capacitors, they mean that you have to use what's called DC balanced signaling. You have to send kind of an equal number of 1s and 0s so that you don't charge up your decoupling capacitors, because then you're going to be receiving things incorrectly at the other end of the link. You're going to get bit errors. So one thing that these line codes will do is ensure that the result has a similar number of ones and zeros. So 8B10B and 6466 use very different techniques for doing this. 8B10B, it's a more deterministic encoding scheme. And as a result, they actually keep track of the running disparity, and all of the symbols are carefully designed so that they have, they have almost the same number of ones and zeros. Some do, some don't, and the ones that don't use the running disparity to select which symbol to send, such that you can maintain the DC level at 0. 6466, on the other hand, it uses the Scrambler, and it puts statistical bounds on the DC wander. So it can't wander more than a certain amount because, you have all of these bits in your LFSR, and it's going to be, you can compute what the probability is of, having a run of ones or zeros, longer than a certain length, in a certain time period. Right. So by putting statistical bounds on that, that's pretty good. And it's not perfect, obviously, but it's pretty good. And it's also very simple to implement at the, in the actual digital logic. So this tends to work pretty well. The other thing that scrambling allows you to do is reduce, EMI, reduce interference. Because if you look at 8B10B, I think 8B10B is actually particularly bad for this, is when you're sending idles with 8B10B, they tend to be very regular when you put a bunch of them back to back. And this can produce some very sharp frequency components, and that can be a problem for EMI. So this is why things like PCI Express will scramble the 8B10B. Even though 8B10B does give you DC balance, they do scrambling on top of that to reduce the EMI. And then finally, the other thing that the line codes do is they ensure a minimum transition density. And this is important for when you're doing, clock data recovery. If you don't have enough transitions, then you can't lock your clock data recovery circuitry. So this is, if I pull up the documentation again for the GTY transceivers, they have a clock data recovery circuit that's responsible for looking at the data and using phase interpolators to align the clock with the incoming data. And this works pretty well, but if the incoming frequency is varying a lot, this has to be able to track that. And the only thing this is looking at is the edges in the data. And if it doesn't have enough edges, then, it's not getting enough information to keep a lock on the data, to keep tracking it. So with 6466, the scrambling does help with this, but the main thing is that the sync header, this forces a transition every 66 bits. So you're guaranteed every 66 bits, at minimum, there's going to be at least one transition. I mean, if you're forcing 0 to 1, then 66 bits later, you have another 0 to 1. There has to be a 1 to 0 somewhere in the middle. Yeah, so worst case, every 66 bits, as long as that's enough for your CDR to maintain a lock, then you're good to go. And then I think when you're using things like FEC, in a lot of cases, they will actually try to, they will try to reuse some of the overhead of the line code for the FEC, and in which case they'll get rid of some of this kind of thing. And they'll just send the blocks directly. And I guess they have enough statistical confidence that they're not going to have a problem with that. Oh, okay. It looks like Vivado is done. So we'll go over to the hardware manager and see if we can get this thing reloaded here. All right, so I'm going to go ahead and program the FPGA, right? Boom. Okay. Takes a few seconds to load things over JTAG. JTAG is not the fastest interface ever. All right, there we go. That looks good. It's okay, I'm getting a link light. All right, let me go ahead and run that. Well, that's not a good sign. Oh. All right. I think I did plug both of these in. Maybe. Not gonna work. Ah, my ILA is not happy. What is going on here? I think I'm running into a reset sequencing problem, maybe. Let me go ahead and I'm going to go reprogram this guy. Oh, not run. I want to reprogram the FPGA. This is one annoyance with the way the GTY Transceiver wizard is set up. They don't have like a checkbox or something to isolate the resets across the different channels. I don't know why they don't do it that way, because that would simplify a few things quite a bit. All right, let's see if my ILA is working now. Nope. All right. I'm gonna try one other thing. Where did I put that thing? All right, let's try that. So I think what's happening here is, since I wired up both PHYs instead of just one, which probably would have been a smarter thing to do, basically both PHYs are getting reset, or both transceivers are getting reset. Rather annoying. All right, let's see. We have 2 link lights now. Yes, I do have 2 link lights. Okay. BIOs, okay, I'm getting block locks on both. All right, cool. Let me go run this. Well, let me just do a force trigger. Okay. There we go. All right, so that is up. Great. Let's take a look at the board. There we go. All right. So you'll see what I did. I inserted a loopback module. All right. So both of these ports are now up. So let's see if I remove this guy. Oh, and the clock has stopped. Yeah, I think I'm running into some sort of a reset issue now. Dang. All right. I was actually thinking about this last night to try to figure out if I can separate the resets on these transceivers more effectively. It's also possible that what's happening is when I assert the reset, it immediately stops the clock, and then the reset doesn't get deasserted. Maybe because I am running in the user clock domain, and if I don't release the reset, then it doesn't start running again. Oh man. All right. Well, what are you gonna do? Let's see. I think this thing is working, or okay. So I got bad block. I got block lock. Oh, hang on. I thought I added so I added these connections as well. So I got a sequence error on the first one. But that's just high. Yeah, so I have this one set up to run on a different clock. Wait, the bad block at sequence error. Yeah, okay. I think I need to do some work on the reset side in order to make this work, because it looks like this is not not going to cooperate today. Well, yeah. Let's see here. So block lock is high, sequence error is high, bad block is high. So presumably that would have triggered the reset. Well, I mean, let me put it to you this way. It seems to be resetting the transceiver, so that's a start. But obviously there's a few things that need to be sorted out. And I think the issues that I'm having now are more related to how the resets are wired up in the transceivers and less about how, the new Watchdog code that I just put together, how that works. So I think there's not much more I can do on the stream today. Suffice to say that it seems like it did try to reset the transceiver. But I'm going to need to do a little bit more work to get things sorted out. And I'm not sure if, let's see, what time is it now? Yeah, this has been going for a while. So if people want to watch me screwing around with Vivado, I guess I could do that. Otherwise, I'll probably close this down, because that's going to take a lot longer. Yeah, oh, and this says that there are a couple of failing endpoints. This is most likely because of the connections to the VIO core. So it says 9. How many VIO connections did I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Interesting. Okay, so yeah, it's just those connections. All right. Well, getting this polished off is probably going to take quite a bit of time, so I think I'm going to go ahead and, well, it's going to take quite a bit of time and probably some significant rehashing on my part to make it work. The other thing that I want to be able to do is to make the transceivers runtime switchable between 10G and 25G. And that's going to require reworking the clock network and reworking and isolating the reset networks a lot more. And that's going to require some experimentation with the DT wizard to figure out, how to generate everything so that's actually going to work properly. That's going to be rather tedious and it's going to take some time. So I'm not going to do that right now. So I think I'm going to go ahead and close the stream down. I've been going for almost 3 hours now. Cool. To everybody who's still listening in, thank you very much. And I guess I will see you guys next time. Hopefully you don't have to wait as long as for this one. Research projects have been ramping back up, and not everything that I've been doing has been, appropriate for streaming in this way. So I'm planning on doing some more of these, but the question is when? We'll see. Anyway, thanks to everyone for listening. Thanks to everyone who tuned in. So I will talk to you guys later.